Hello, my name is Michael Glinsky of BNZ Energy Incorporated. I'm going to present to you the content of a manuscript entitled High Gain Fusion Target Design Using Generative Artificial Intelligence that is out on the arXiv and will be submitted to physical review letters. We are returning to topological basics. The topic of my UCSD oral qualifying exam in theoretical plasma physics. The examination committee, chaired by Marshall Rosenbluth in the second floor Mayer Hall conference room. Inspired by Ted Frankel's class in the geometry of physics and in collaboration with Michael Friedman. This is Taylor relaxation to a topological singularity with helicity conservation as energy, the weak Noether invariant, is dissipated to an external system. This is only a metastable point, an X point, so that the system needs to be ponderomotively stabilized. The X point is a local maximum that can be stabilized. Topology can be viewed as the mathematics of knot tying. Think about tying the knot as shown. Take two strings, tie one string into a loop, twist the second string around the first, tie the second string into a loop. Now deform the knot, the manifold, into a double helix, two counter-rotating double helices, and a torus. The double helix is the deformation of a Z-pinch plasma. The two counter-rotating double helices are the deformation of a laser reverse field pinch, RFP, to be discussed in detail next. The torus is the deformation of tokamaks and stellarators. This should look familiar to those of you familiar with the deep reinforcement learning, DRL, or the deep Q networks, DQNs, used by DeepMind in the AlphaGo and AlphaFold products. How do you tie the plasma in knots and keep them compact? This is the job of Ubuntu Fusion target and drive design. Shown on the left is what happens if the plasma is not tied in a knot, that is, it has no helicity. To its right is a plasma in a Z-pinch that is tied in a knot, that is, it has helicity. On the right-hand side is the target and drive of the proposed laser Z-pinch. Shown is a cylinder of beryllium coated on the inside with a solid fuel that, while more challenging to ignite than DT ice, is capable of giving significantly more yield. On the inside is a DT gas igniter that will be compressed by the cylinder as it implodes, driven by the magnetic pressure generated by the absorption of the laser in the candy cane stripe pattern, shaped by the appropriate phase plates. The stagnation of the igniter will be the twisted pair of strings, 20 microns in diameter, separated by about 200 microns, with axial spots about 5 microns in radius, shown by the orange image that is a self-emission image from the Z machine. The image shown is prevented from forming the spots because the plasma is preheated by a laser to 300 volts. The two strings of the stagnated igniter will be surrounded by the tornado of the cylindrical shell of the solid fuels about 800 microns in diameter. The tornado shown was generated by Dolly, and to the right of the core shown as a backlit image of the Z-pinch plasma at the University of Michigan. Since there is a very efficient, that is, with a very high implosion velocity, stable 3D spherical implosion of the igniter, the solid fuel will be able to ignite and burn the solid fuel, first in a spherical manner until the spot coalesces, then in a cylindrical manner. Shown on the right-hand side is the knot tied in the plasma. There will be very large helical magnetic fields at stagnation in excess of 10 kilotesla, reducing the radial heat flow and alpha transport. The dimensions and shape of the target and the pattern, spatial and temporal, of the laser will be designed by Ubuntu genAI to optimize the yield. Let's take a closer look at the details of the laser drive. Shown on the left is the drive of the laser Z-pinch shown on the previous slide. Shown on the right is the more practical laser RFP. 4 laser beams shaped by phase plates about 1 centimeter in diameter impinge on the target in a plane perpendicular to the axis of the target cylinder from the north, south, east, and west. Therefore, there needs to be no physical contact with the target to deliver the energy, and only 4 very small access ports. The Z-pinch geometry does require 2 handles on the target to provide a path for the return current, complicating the target and making it more difficult to fabricate. There also needs to be no conductor across the top and bottom, further complicating the target and making it even more difficult to fabricate. The base layer illumination pattern is a helical candy stripe. The RFP geometry does not require the handles for the return current. Instead, a beryllium top and bottom needs to be put on the cylinder, making it into a can. The base laser illumination pattern is a crisscrossing double candy cane. Note that this target will be at room temperature, not at cryogenic temperatures, making it much more practical. The target is simply a low tolerance to about 2% can, with top and bottoms coated on the inside with solid fuel and filled with DT gas, in the case of the laser RFP. This is an extremely simple, practical target that is very easy to fabricate. Here are the 10 pieces of evidence, 6 of them published, heretofore unexplained by theory, supporting the theory behind Ubuntu Fusion target and drive technology. This is similar to how the special theory of relativity explained the Michelson-Morley experiment. The stagnations of the maglev experiments always form a twisted pair with an axial sausaging, but only if the plasma is driven to have a significant amount of helicity. The plasma is compressed from the initial 1 centimeter dimension to 2 helical strands about 20 microns in diameter, separated by about 200 microns, a convergence ratio of 200. This can only happen if there is an inverse cascade leading to self-organization. There is a 10 times variation of yield for nominally similar Z-shots. This is probably due to small variations in target and drive that seed the natural topological modes. There is better performance for large aspect ratio targets because natural topological modes are probably growing faster. And there is poor performance of the dielectric coated targets because natural topological modes are probably growing slower. Experiments at the University of Michigan have tracked the mode merger and the inverse cascade. The last 5 pieces of evidence can be found in simulations. The data science group at Lawrence Livermore National Laboratory, when they optimized the 2D laser ICF target design, found that the optimum metastable design was a laser RFP yielding a quadrupole stagnation consisting of 4 vortices. A group at the Laboratory for Laser Energetics, when they simulated their hybrid laser target in 2D, found that they achieved a laser RFP stagnation. A group at the Osaka Laser Lab, when they simulated a short pulse laser target in 2D, found that they achieved an RFP stagnation. Shipley et al. At Los Alamos National Laboratory, when they simulated an automag Z-pinch in 3D, found that it had 2 times the yield of an equivalent maglev target. Finally, Glinsky and Maupin, when they simulated an ensemble in the 2D plane perpendicular to the Z-pinch axis, found that the stagnation always consisted of 2 vortices, whose orientation was set by the initial m=2 perturbation, no matter the size of that perturbation. And there was an inverse cascade consistent with the Z-pinch twisted pair topology in 3D. Note that the self-organization in the 2D simulations came from the conservation of the vorticity topological invariant. To maintain metastability in 3D, the target or drive will need to be twisted in the axial direction in order to have the helicity topological invariant. This design philosophy leads to more aggressive high AR targets, no suppression of natural topological modes by a dielectric layer or a dynamic screw pinch, no laser preheat of the DT gas so that the gas implodes on a much more aggressive adiabat, more efficient use of the drive energy since the drive energy is concentrated at the natural topological modes, much better ignition and burn propagation, burning the more efficient and practical solid fuel instead of DT ice, low tolerance and simple targets for inexpensive target fabrication, and no turbulent mixing due to the inverse cascade. As stated by DeepMind in A Hitchhiker's Guide to the Galaxy, it is most important to know what the question is, not the answer to the question. The following series of slides are a series of questions. Tom O'Neill, when he taught the graduate E&M course, taught the course from the perspective of Landau and Lifshitz, not Jackson. We need to approach fusion target and drive design from the perspective of nonlinear, not linear plasma physics. We need to be good parents and encourage the plasma to mature and become its own person. The current theory of artificial intelligence, based on the work of John Hopfield, views AI as a web of connections of nodes organized into layers with the connections, graph edges, connecting one layer to the next. The system is assumed to be in statistical equilibrium and is called a Boltzmann machine. I don't know. Do you know what this is? I don't. Instead of using this graph paradigm, we view AI as model estimation by a piecewise linear universal function or functional model that is estimating a function or functional with C1 continuity, but no more. That is, it is a minimal surface with singularities. This model has thousands of parameters for a function and trillions of parameters for a functional. But for a functional, that is not near enough. The system is assumed to be canonical in only dynamical equilibrium, not in statistical equilibrium. It is a question of physical kinetics, not statistical mechanics. The concept of dynamical equilibrium and the evolution to a statistical equilibrium was taught to me by Tom O'Neill in the graduate plasma physics course he taught at UCSD. What is the functional and function that generative artificial intelligence is estimating? It is the action, also known as entropy, log likelihood, the approximate Q function of DeepMind's AlphaGo and AlphaFold, and the approximate score function of OpenAI's ChatGPT. The functional is the canonical generating function of a canonical transformation from the canonical field momentums and fields of the collective system to the canonical momentums and coordinates of the system, that is, the reduced order model. The function is the canonical generating function of a canonical transformation from the canonical momentums and coordinates of the reduced order model to the canonical momentums and coordinates where the evolution is linear. The modern systems control theory of Kalman and Bellman, developed in the late 1950s, is based on the Hamilton-Jacobi equation. We extend their theory to collective systems and the functional form of the Hamilton-Jacobi equation. The Bellman equation, as the Hamilton-Jacobi equation is called in systems control theory, is solved in the deep Q networks of deep reinforcement learning, DRL, of AlphaGo, as indicated on the first slide. Current genAI solves the Hamilton-Jacobi equation by introducing a significant amount of diffusion that drives the system to statistical equilibrium. They call this a diffusion model. It solves for the ensemble in statistical equilibrium by using the metropolis, better known as the Rosenbluth method. This significantly degrades the performance. It sacrifices performance for stability and solvability. Conservative systems have as many unstable roots as stable ones. The unstable x-points or singularities are the desired ones, but they are destroyed by this very heavy L2 regularization. Instead, we calculate the singularity spectrums by calculating the coefficients of the functional Taylor expansion of the action, also known as the X matrix, M-body scattering coefficients, and M-body Green's functions. We derived a formula for this functional that has a fast n log n computer implementation of the forward and inverse transformations. It has the form of an iterative wavelet transformation interleaved with the Green's function of a complex variable. This is new, the Heisenberg scattering transformation. It is a logical mathematical process of renormalization based on calculating the S matrix of Heisenberg's canonical approach to quantum field theory. It is a non-stationary, that is local, Fourier spectrum, or the non-stationary spectrums that are the solution to the renormalization group equations. The HST has the structure of a deep convolutional network. It is a series of convolutional layers interleaved with an activation function. The results are then pooled to form a reduced order model. Each convolutional layer scatters the signal. The HST can be viewed as the multiple scattering of a signal to all orders. This is the transformation, the transformer that a generative pre-trained transformer, GPT, is pre-training. The African philosophy of Ubuntu is based on the interconnectedness that leads to a conservative system with canonical structure that is a symplectic geometry. Given this logical mathematical process that is Ubuntu genAI, the collective system, the society, can be controlled. The topology of the plasma can be optimized and stabilized. Another way of looking at the HST is as a deep deconvolution of the multiple reflection of the individual, the spirit of Ubuntu, who is multiply reflected into the collective, that is, society. By the way, collectives are fields or swarms of elementary particles, making elementary fields, charged particles making plasmas, molecules making fluids, celestial bodies making cosmoses, economic entities making economies, persons making societies, and so on. Generative Artificial Intelligence, genAI, is a two-stage canonical autoencoder that is a controller of collective systems. Its input is a measurement of the fields, and its output is the force field of control. The first stage is the HST, followed by a principal components analysis, a PCA, giving the reduced order model. It is not a deep convolutional neural network with trillions of parameters as in the DQNs and GPTs. The second stage is a multi-layer perceptron, an MLP, with rectified linear unit ReLU activation with thousands of parameters that estimates the canonical generating function. This forms the two-stage decoder. It is followed by a two-stage encoder. This approach to AI is solving a system of partial differential equations by a functional transformation to a domain where the motion is trivial, that is linear, then transforming back. The circuitry of the HST plus PCA is most likely found in the primary visual cortex of the brain, and the circuitry of the MLP with ReLU is most likely found in the prefrontal cortex of the brain. The core innovation is replacing the deep CNN of genAI, which has trillions of parameters, with the HST, which does not have any parameters. The resulting Ubuntu genAI is a controller of collective systems that optimizes the performance of the collective system and ponderomotively stabilizes the collective system so that it does not disrupt. Glinsky and Maupin were able to train an MHD surrogate using a preliminary version of this new theory in 20 core seconds using 500 2D simulations. The high-fidelity surrogate could simulate the system in 1 core second, where traditional finite element methods would take 240 core hours. For a 3D simulation, traditional methods would take 100,000 core hours. The singular value decomposition of the cross-variance matrix showed a one-to-one mapping between the PCAs, that is the renormalization spectrums, and the initial conditions. A remarkable result that gives physical meaning to the renormalization spectrums. This is another whole talk. See the links to the paper on the arXiv and the links to the YouTube video of the talk. The HST is a logical mathematical process of renormalization as requested by Dirac. There is another whole talk about how this is a new theory of plasma physics and a new field theory. It is an alternative to the BBGKY theory of plasmas and the perturbation theory of fields, both of which makes mistakes. They expand the terms of the mirror cluster expansion in terms of the plasma correlation parameter and the field coupling parameter. The convergence goes from superconvergent to a very weak asymptotic convergence, leading to the divergence, the infinities in current methods of renormalization. The expansion parameters are, many times, not less than 1. See the links to the paper on the arXiv and the YouTube video of the talk for the details. A postscript. Ubuntu genAI is a very powerful tool in model estimation. This emanates from the linkage of the form of the Lagrangian, function and functional form, and the non-stationary spectrums that are found by the HST plus PCA. The one-to-one correspondence. There are only a limited number of terms that can appear in the Lagrangian, so that there will be a limited library of non-stationary spectrums. And by cross-correlation, as was done by Glinsky and Maupin, to the coupling constants, that one-to-one correspondence can be found. This is further evidenced by the transfer learning of the pre-training of a GPT from language to fluid dynamics, for instance. Now, when the theory is compared to experiment, one can determine the number of non-stationary spectrums and what those non-stationary spectrums are in the experiment by determining the number of significant principal values and determining the principal vectors that are associated with those significant principal values. One can also do the same exercise with the theory. Discrepancies between the theory and experiment will show if a term is missing in the theory or if a term is incorrect in the theory. The theory should extrapolate very well in the scale of the fields, just so that the experiments are being extrapolated away from the non-stationary singularity spectrums in the theory, not extrapolated towards a non-stationary singularity spectrum that is not in the theory. There is a simple test for this. Conduct a series of experiments at different scales of the field. Examine the systematic deviation of the experimental results from the theoretical predictions. If the deviation gets less as the scale moves in the direction of extrapolation, then the theory is sufficient. If its deviation gets more as the scale moves in the direction of extrapolation, then the theory is deficient. Thank you very much for listening.